So my talk is on gravitational waves, and it's part of the ASRAS forum. And at the start, I wanted to say that in putting this together, both in the research and in the construction of it, in fact checking, and in a couple cases in graphics, I made use of a AI assistant, and it was pretty good to the point where I would almost call it a collaboration for putting together this presentation.
Hey Jeff, before you get going, could you put it back into presentation mode? We're seeing your whole, we're seeing your whole slide deck. Can you put it in presentation mode? Thanks.
Yeah, I can do that. I was planning to actually. I just really hadn't started yet. Just talking about the. So anyway, so I made use of an AI assistant, and it's pretty interesting. If you'd ever want to talk on how I made use of it, that might be a possible future talk for you. Okay, so massive objects warp space-time, and as a result of that warping, the path that both matter and light travels is affected. And light will travel through space-time at the speed of light along what is called a geodesic. And a geodesic is the shortest possible line of travel on a curved surface. Gravitational waves are ripples in space-time, and we'll see why later, but the nature of the ripple is such that you simultaneously get compressed in one dimension and stretched in the other direction. And if you think of that compression and stretches happening in a plane, then the direction of propagation would be perpendicular to that plane. So compress and stretch are perpendicular to each other, and together are perpendicular to the line of propagation. So in this case, I show gravitational waves moving towards the Earth, and if when they encounter the Earth would be periodically squeezed in one dimension and stretched in the other, and then vice versa. So what I'm going to do in setting up this talk at the start and the middle is I'm going to make use of a couple conceptualization tools that I put together to aid in our understanding. And one involves 4 impossible but instructive scenarios, and one will involve what I call a sky patch localization ladder. The impossible but instructive scenarios will be a vanishing sun, a sun collapsing into a black hole, a static egg-shaped star, and a rotating egg-shaped star. So we're working our way towards understanding gravity waves with these. Okay. Yeah, this is still going to be a problem here. I need to get that. Okay. Okay. So I think where we were is the Earth gets periodically stretched and squeezed by the gravitational wave. And I'm going to have those 2 conceptualizing tools, one with impossible scenarios and one with a sky patch ladder. So the first scenario is the impossible case where the sun just vanishes. It's gone. It's not there anymore. And from the Earth, if that happened, it would take about 8.3 minutes for us to realize that happened, because we would continue to see sunlight for 8.3 minutes, because that is how far away the sun is 8.3 light minutes from the Earth. And once that happens, not only once we no longer see the sun, we will also no longer feel the effects of the sun's gravity, so that the Earth it will move in a line tangent to the last point in its orbit at which it felt the sun's gravity. Likewise, the case with Venus, likewise, the case with Jupiter. But the interesting thing is, and this will be important to a later discussion, is that from the Earth, we will still be able to see Venus because we see Venus through reflected light. So it will take 6 light minutes for the sun to reflect off of Venus, and then depending on where it is on its orbit, up to another 8.3 minutes for the light to reach us. So the sun vanishes in 6 light minutes. Venus no longer sees the light from the sun. In 8.3 light minutes, we no longer see the light from the sun. But for a while, we still see Venus. And for a while, we still see Venus in orbit until after about 14 minutes. And then we no longer see Venus and we don't see it orbiting. And with Jupiter, it would take an even longer period of time. So the important takeaway from that is light from the same event can arrive at the Earth at very different times. And again, that'll become important to a concept that we'll explore later on. Okay, so the next impossible situation is that the sun suddenly and symmetrically collapses into a black hole. In that situation, since it's a black hole, it's not radiating light out to us. We will not see the sun, and the scenarios that I just described in terms of being able to see the reflected light off the planets for a while after would still apply. But what doesn't apply in this case are the gravitational effects. The gravitational effects are actually the same because the mass of the collapsed sun is still the mass of the current mass of the sun, so our orbit will be the same. I guess I talked ahead of the chart I'm on, so it didn't make sense to you. Back to the instructive scenario 1, I also made mention here that each of the planets will experience a tide, a sun-induced tide. I've exaggerated the extent of the bulges, but I just wanted you to know that each planet will be, the solid part of the planet will be affected by the sun's gravity, and it will be elongated in one dimension, and then perpendicular to that, everywhere perpendicular to that, it will be compressed. And those are tidal bulges that can be described by a mathematical construct called a quadrupole. In the case of the solid Earth, the bulge for the side of the Earth facing the sun will be about 10 centimeters. You don't notice it because everything around you is also being raised by that bulge. And then on the opposite side of the Earth from the sun, you will also get a bulge of the solid Earth. So I'm not talking about the water tides, which are much more dramatic. I'm talking about how the solid Earth is affected. Okay, in the real case of the Earth, we have both the moon and the sun creating tides, and in reality, the effect of the moon is far more dramatic. We're just considering the case of the sun only, just for conceptual purposes. The tidal strain is This is like the only equation that I'll show you, at least for a while. It's a fairly easy equation. You just take the change in your length and divide it by the original length. So that's an equation that you can use to calculate what they call the tidal strain. And in the case of that 10 centimeter rise of the Earth's surface, a tenth of a meter, what it says is that the tidal bulge only lengthens the Earth by about 1 part in 63,710,000. So it doesn't move it much, but still 10 centimeters is something you can visualize. So the impossible but instructive scenario 2 is the case where the sun collapses symmetrically into a black hole. Can't really happen because the sun's not massive enough to do that, but it's useful conceptually. The light travel times, as I was mentioning, will be the same as they were in the previous example. However, in this new scenario, all the planets remain in their original orbits. The mass of the black hole is the same as that of the original sun. Outside the sun's radius, the gravitational field depends only on the total mass, not on whether the mass is a star or a black hole. And as an aside, the diameter of a 1 solar mass black hole would be about 3.7 miles. The tidal bulges depend on the sun's mass and distance, not on the physical size or internal structure. So even though the sun has collapsed, the gravitational field at 1 AU is unchanged, the tidal field at 1 AU is unchanged, and the quadrupole deformation of the Earth, that is the tides, is unchanged. Because the collapse of the sun is symmetric, no gravitational waves are produced. Each planet remains in its original orbit. Each planet maintains its original tidal bulge. So now for impossible but instructive scenario 3, we're going to consider a static egg-shaped star. Stars don't really tend to want to pull into spherical shape, so an egg-shaped distribution is not something that would happen. I asked the AI assistant to create a gravitational well around the egg-shaped star, and it somewhat was able to do it, but you can see that it isn't perfect. But the gravitational well around the star should take on an egg-shaped appearance near the star and then eventually flatten out into flat space-time as you're getting farther away. And this is a static egg, so there's no gravitational waves. And then I asked it to create a rotating egg-shaped star, which I tried very hard to get it to actually rotate the egg, but it couldn't figure out what I was telling it. So what I want you to do is visualize that if we have an axis through the short dimension of the egg and we're rotating about that axis, I want you to visualize that the distribution, the well around that egg would shift in shape and maintain an egg shape as the star rotates. But those changes that it would make to catch up would happen at the speed of light. Because the shape of the space-time fabric is now changing, we have a gravitational wave. And a quadrupole is the physical arrangement of the mass while what we call the quadrupole moment is a mathematical description of that arrangement's non-spherical nature. So if we have a spherical quadrupole, we would not have any quadrupole moment. It would be zero, and all the other cases would be non-zero. So I'm going to present a few cases for you to conceptualize. The most extreme case would be if you have two compact masses that are co-rotating. In that case, you're going to have a very large quadrupole moment. And examples of those would be black hole binaries, what we call compact masses, neutron star binaries, white dwarf binaries, and mixtures like black hole neutron star binary. It looks like I have a typo there where I should have a BH instead of BN. So those would produce very strong gravitational waves during mergers. This is not really physical. The next one, a cigar-shaped rotating mass, but it would have a large positive quadrupole moment. It likely doesn't occur in nature with large masses. If it did, it would have a very strong gravitational, produce strong gravitational waves, but not as strong as those for the black holes. If you have a nearly spherical rotating mass, then you're going to get really weak gravitational waves, but you would get some. And those could be planets with tidal bulges as they revolve around the sun, very, very, very weak. Or neutron stars with what they call tiny mountains. So they're neutron stars that are spinning, but they're not completely spherically symmetric, so that they cause tiny little ripples in space-time. If you have a perfectly symmetric, uniformly rotating mass, you will have zero quadrupole moment and hence no gravitational waves. So a very symmetrical star would fit that category. The positive and negative for the quadrupole moment isn't really that important to us, but it would affect the phase of the gravitational wave produced. So if you had a pancake-shaped mass distribution as opposed to the cigar-shaped mass distribution, you would get essentially the same situation where you would produce strong gravitational waves, but you would have a phase difference in those waves. And then another situation that you could have is a chaotically moving, chaotic mass distribution where masses are flying off in different directions at different angles, perhaps spinning at the same time. You're going to have, I called it fractionated moments. It's probably better to think of it as lots of very smaller dipole moments. So that kind of chaos you could get from supernova explosions, kilonova explosions, or the superposition of GW from gravitational waves from many events across space and time. All those will give you a signal that is chaotic, which in science terms you would call a stochastic signal. You would have weak, incoherent gravitational wave signals, and you have to do a lot of work to extract pieces out of that signal to get information. So the shape of the signals that you get for compact masses that are headed towards merger but haven't gotten it yet, you're going to have rising frequency and amplitude. And these could be either black hole binaries working towards merger, or neutron star binaries doing that, or white dwarf binaries doing that, or again, a mixture doing that. You can get a continuous sinusoidal wave uh, from some different scenarios. In the case of black hole binaries, very early on, before the in spiral really gets going, there can be a long period of time where it's almost symmetric. The orbit almost stays the same for a long period of time, and you can get a continuous signal for that reason. But you can also get a continuous signal with a neutron star that has the little quote unquote mountain on it. As it rotates, it can create a signal, a continuous gravity wave signal, gravitational wave, I should say. Gravity waves are a different thing that has to do with atmospheric densities. So the if it's caused by compact masses that are rotating, you're going to have a somewhat strong signal. If you have a case of the mountain on the neutron star, it's going to be a very weak signal. In the case of the perfectly symmetric star, there is no gravitational wave, so it's flatlined. And chaotically moving chaotic mass distributions are going to give you a stochastic signal. Has a random appearance, but if you can pull it out, there is underlying information. And then I didn't really picture in the previous chart, but you can also have what they call burst, which are spikes in the gravitational wave. And they can happen for a number of different reasons, including supernovas, some mergers, and kinks in space-time even. So stochastic gravitational waves contain relic gravitational waves from the early evolution of the universe, as well as information from more recent events. We're getting gravitational wave information from all across space, all across time. And this is an example of a grossly exaggerated neutron star mountain, showing that you would get a continuous wave out of that. In spirals produce the strongest waves. And again, as it's headed towards in spiral, you're going to get as it's getting closer and closer, it's going to be orbiting faster and faster. So the frequency goes up, and the strength of the wave is going to get stronger so that the amplitude increases. And if we're trying to monitor a continuous gravitational wave using one of our detectors like LIGO, is not going to appear continuous in the detector because the Earth's rotating and it's also moving around the sun. And so you're going to have a signal, you're going to have signals superimposed on what would otherwise be your continuous signal. So it's like modulation. You have amplitude modulation that you might be familiar with from radio. Are there any questions yet from to this point? Okay, so black hole mergers produce the strongest gravitational waves, and the strength of the gravitational wave is the strongest. I tend to speak loud too. Am I overdoing it? Okay. Gravitational waves tend to be the strongest when both black holes have the same mass. They become weaker when there's a big difference between the masses of the black hole. In fact, when the smaller black hole is very much smaller, the gravity well of the combined system approaches that of the bigger black hole. Similar to how, like if a planet is orbiting the sun, it's not really affecting the sun's gravity well that much. And the signal that you'll get, what we call a chirp, similar to the chirp that a bird would make, is not only the ramp up that I was talking about already, but eventually when the merger occurs, you've got some dramatic action happening, and then once that merger's finished, the waves, the gravitational waves dissipate in what they call the ring down. So if you look at the top above the chirp signal, you'll see the two black holes spiraling in together, and a graphic of the merger, and then the final larger black hole. And so those phases are the in spiral, the merger, and the ring down. Now, if you imagine a circle of free masses in open space, they will react to, how will they react to a passing gravitational wave? The direction of propagation is perpendicular, and it imagines the wave is moving in perpendicular to our screen. It's going to alternately compress in one direction and stretch in the other, but which appears to make the circle move, but what's really happening is space itself is alternately squeezing in and stretching. So the little masses are in for the ride. And if the Earth were inside a region, so if you can imagine that going on the left pane, and then just continue doing that as it propagates through space, you can imagine something like the diagram that we have here. And again, if the Earth were to be inside the region, it would alternately be squeezed and stretched. So so would, by the way, the arms of an Earth-based gravitational wave detector like LIGO. And in the case of, we call those gravitational wave detectors interferometers. We'll see later, because it interferes with the laser waves that go through it. But in the case of those detectors, one arm stretches and its perpendicular partner shrinks. We have a number of gravitational wave detectors that are land-based right now. The biggies are the LIGO detector in Hanford, the LIGO detector in Livingston, and the Virgo detector. There is a smaller detector called GEO 600, which is used for concept testing, but some operational support. And then there's Kangra, which had been operational, is undergoing some upgrades and will be operational again. And then scheduled for operation by the year 2030 is another LIGO, which will be based in India. So again, we're going to consider a circle of freestanding particles in space. What I want you to notice, if you look at each circle, you're going to see the flexing, and that's what draws your eyes. But now let's, instead of looking at the circles themselves, let's focus on an individual particle within that circle. And what you're going to find out is that the particle will move along a fixed horizontal line and also along a fixed vertical line. That is one type of orientation that it can have. Another one would be rotated 45 degrees relative to that. And then if you notice that each particle moves along a fixed line at 45 degrees and also along a second line perpendicular to it. So we have those two scenarios that are essentially the same as each other, except they're rotated by 45 degrees. We call those two cases plus polarization and cross polarization. And to think about these particles that are experiencing these waves, a good analogy to think as they're bobbing and weaving through space is to think about how a buoy or a fishing bobbin maintains its general location, but traces small circles in response to a passing water wave. If you have a cohesive object, like a planet, the whole object undergoes tidal deformation, showing up as alternating stretching and compressing along the perpendicular directions. And we'll talk a little bit about polarization later. For now, we will just consider the perpendicular stretching and compression. To capture a light wave, and a lot of you know this because of your interest in astronomy, to capture a light wave with an optical telescope, the mirror must be comparable to or a larger wavelength. I don't think I have a mistake in that sentence, but the wavelengths, in order for you to see through a telescope, the wavelength has to be really smaller than the diameter of the mirror of the telescope in order for that to work. Okay. However, in the case of water waves, you don't really need to capture a full wave to get information. You can consider the timing of a bobbing buoy or a bobbing fishing bobbin. As they go up and down, you've gone through a cycle, so you know the frequency. Likewise, we can know the frequency of a gravitational wave without capturing the entire wavelength by timing the cycle of stretching and compressing in the detector. If we want to know the wavelength, we can compute it, but we don't need it. The timing gives us all the information that we need to make use of the gravitational wave. And the bottom graphic, it was not really possible for me to do with it what I wanted to do with it, so you have to use your imagination. What I want you to see there is that one arm of LIGO is 4 kilometers long. So the little yellow box represents one arm of LIGO, and it can capture wavelengths from gravitational waves. It can capture information from gravitational wavelengths. Gravitational waves that have wavelengths that are much larger, thousands of times larger than the length of the arm of LIGO. And it does it because it's doing timing measurements, the up and down measurements, and it doesn't need to rely on capturing the wavelength. So my second conceptual device that I want to use is I want to create a sky patch ladder to get an idea of what area of the sky we might be able to see under various conditions with various gravitational wave detectors. And the sky patches that I'm going to use are a full sky, which is about 41,000 square degrees. The constellation Ursa Major, which is on the order of 1,300 square degrees, Orion about 600 square degrees, the Summer Triangle around 400 square degrees, Then on the smaller scale, the Hercules globular cluster. I stayed up last night for a while because I hadn't gotten, I was doing the final crunch to get this done. And so right now I'm feeling the effect of it, and that's why I'm tripping over my tongue. The Hercules globular cluster would have a sky patch of 0.11 square degrees. Mizar and Alcor about 0.04 square degrees. Albireo A and B, the golden and blue star, about 0.0001 square degrees. And subarc second would be smaller than, I'm not going to say you can see the number of zeros. Okay, we will attach gravitational wave events and detectors to it as we go forward. So the entire celestial sphere covers, again, around 41,000 square degrees. It will cover cases of all sky uncertainty, or it will also cover cases where the signal is an all sky signal, so all sky backgrounds. Topics of potential interest at that scale: cosmic backgrounds, deep time signals, inflationary gravitational waves, and it's the realm also of relic neutrinos. Ursa Major covers about 1,300 square degrees, which is about 3% of the total sky. There is a type of detector called a pulsar timing array, and those localizations could be of that scale. And if we have a LIGO constellation, which is really how many LIGO detectors are involved, if we use just two of the detectors, the one at Hartford and the one in Livingston, and don't use a third detector to have triangulation, then there's a relatively large patch in which we have to try to localize an event, and it's on the order of the size of the constellation of Ursa Major. And it also involves detections of nanohertz gravitational wave backgrounds. Orion covers about 600 square degrees, typical of sky patches for LIGO and Virgo being used together. So in that case, you have three detectors in the constellation in a triangular fashion so that you can do some triangulation. Speaking of triangles, the summer triangle covers about 415 square degrees, and it's in a transitional scale between PTO and LIGO regimes. And there are large multi-detector uncertainty regions involved in that. The Hercules globular cluster has an apparent diameter of about 20 arc minutes, which is about 1/3 of a square degree. And so it's about 0.11 square degrees. And I don't have anything attached to it, but I want it as a frame of reference for you to think about in terms of that scale. Obviously, we're going downward in scale, so we're looking at smaller and smaller patches of the sky. Within Ursa Major, we have a double star. It's really, I think there's up to 6 stars in the system, but what we see with our eyes is a double. Mizar and Alcor, they're separated by about 12 arc minutes, about 1/5 of a degree. So the patch size is about 0.04 square degrees. And that would be using LIGO and in a counterpart in the electromagnetic spectrum. An example of that would be, say, the case where you had two neutron stars that merged and created a violent explosion called a kilonova. The sky patch will become smaller than it would otherwise have been because we now have the electromagnetic information to help us localize still further. So we're using the three detectors, LIGO, LIGO, and Virgo, and information from the kilonova to further localize. Okay. The Albireo telescope double, again with Albireo A being gold and B being blue, are about 35 arc seconds apart, which is about 1/100th of a degree. So the patch size would be about 1/10,000th of a square degree. And that's a precession that LISA can get, particularly if LISA is using information that Gaia has collected, kind of a database of astronomy parameters. And sub-arc second diameter would be, an arc second is 1/3600th of a degree, so the patch size becomes very small. And that's the realm that future missions might be able to do. So you would have localization of perhaps a host galaxy for distant GW events. We don't currently have that capability. That's for the future. Okay, so putting some ideas onto the sky patch scale. I'm providing in the middle column characteristic timescales, and then to the right, the physical phenomena that are being explored. With the full sky, you go through billions of years of cosmic history, things like cosmic strings, stochastic backgrounds, inflationary relics, phase transitions, supermassive black holes, population history, all the buzzwords that you hear about for the early universe. For Ursa Major size patches, the timescale for those events, years to decades, the wavelengths of the signals detected by what they call pulsar timing arrays would be in the nanohertz. And these can involve supermassive black holes, binaries, which are merging, galaxy-sized dynamics. Orion-sized patches, seconds to minutes. That's, again, the localization that two LIGO detectors can give you. And it's the realm of binary black hole mergers. So when we only had two LIGOs working together and we got that first detection, we didn't know exactly where it was. It would be somewhere kind of within the size of Orion. The summer triangle, you're making it even smaller. That would be if you're not using just the two LIGOs, but also LIGO and Virgo. And for Alcor Miser size patch, binary neutron star mergers with, again, electromagnetic counterparts. So you're getting the localization because of the kilonova that results. In the Albireo separation, the characteristic timescale would be hours to 2 days. And once we get a space-based detector called LISA, it's going to look at black hole inspirals and what they call extreme mass ratio inspirals, and it will determine orbital precession. The EMRIs are going to be a fascinating tool, which we'll talk about closer to the end of the talk. Arc second scale, months to years. Again, that's where we're going to be able to detect things which are happening within a particular galaxy. So we will be able to identify the host galaxy, the galaxy in which that happens. And it will be the cosmology of standard sirens. So just as in light waves, you have a cosmic distance scale, which we have various rungs depending on how you're estimating the distance between stars or galaxies. Gravitationally, as you redshift, it affects the signal because the gravitational signal is going to stretch. So you're really listening to a sound, and we're going to call that a siren. So depending upon what the frequency of that siren is will give us information that could be pinned to a distance scale. In subarc second, years to decades, and that's going to be, again, Gaia, SKA, pulsar timing, and PTA refinement for the pulsar timing array. So interestingly, gravitational wave astronomy spans 15 orders of magnitude in time and 8 orders of magnitude in angular scale. So each of these diagrams represent the entire universe. So that was our big patch, the big patch being the entire sky. But here we're representing the entire universe at in three different slices, if you will, or 3 different snapshots. One being the very early universe, one being the snapshot, which was more not instantaneous, but like over a period of a few thousand years, which is sort of instantaneous, called the recombination era. And what happened then is that the universe, as it was expanding, finally got cool enough that electrons and protons could combine to form atoms. Before that, things were too hot. They weren't really able to do that. And up until that time, until they combined to form neutral atom, you had charges that were constantly scattering photons of light. Once we formed the neutral atoms, then the photons were able to travel straight. And from that point on, they could go on a straight line all the way to our telescopes. So the effect looking backwards is, if we look backwards to that time, we can see backwards, we can see what's going on backwards until we get to that recombination time. And then it's like a fog you can't see through because the light is just being scattered. So that is the physical limit for what we can do with light, which has been our main source of information about the sky, both in terms of using it as a telescope to get images, and particularly in the case of getting spectrums from which we can get a wealth of data. We can't see inside of that distance. And the universe was already about 300,000 years old at that time. So gravitational waves are undulations in space-time itself. They don't care about the recombination era. They can see right through it into the very early universe. But we're still trying to figure out what's going on in that very early universe. So it's kind of a gray haze to us. Now, there is some patchiness that we could probably ascribe to it, but that's what we want to find out with 2 multi-messengers that are in our arsenal. the one being gravitational waves, and the others being neutrinos. Neutrinos are able to see further back. Gravitational waves, the furthest back in time. Okay, and then I show our current universe, and you kind of see the outlines of some of the constellations there. This graphic, I think, overdoes it. This is borrowed. I think they overdo the size of their stars, but I'm tempted just to call those pulsars. But that graphic is to represent our current day universe. And we would look out beyond those constellations into deep space to get more and more information. Okay, so the size of the observable universe at the very early epoch was about 10 centimeters across, about the size of a grapefruit. And if we're exploring in that region, there's a wealth of information, everything from cosmic strings to information encoded about inflation. And we could test physics at energies far beyond any particle accelerator. Our Earth-based particle accelerators are amazing instruments, but there's no way that they can create the densities that you would have in the heat and density that you would have at this very, very, very early stage of the universe. At the time of recombination, the universe was about 42 million light years across. And at the current epoch, the observable universe, and I want to be careful to say observable universe in all these cases. The observable universe currently would be about 93 billion light years. So we have to look back in time like that. The messengers that we have are electrons that combine with nuclei to become transparent. We have the visible light finally decoupling to give us cosmic microwave background radiation. And we have the entire universe. It would be all the stars and galaxies, and black holes, neutron stars that we see today. Okay. The relevance to gravitational waves I provide in each of these epochs. I'm not going to read the whole things to you, but again, the important thing, one important thing to realize is gravitational waves will pass through the barrier that the light encounters. So what we call the cosmic microwave background radiation is the radiation at that time, 300,000 years after the Big Bang, in which we could first start seeing light. So if we look backwards, we see some patterns in that fog, which provides some information. And then for the full sky, of today, the relevance to gravitational waves would be, well, that's the domain that LIGO, Virgo, Cagra, and soon the Cosmic Explorer and Einstein Telescope are investigating. These are the events that are happening throughout the sky at our point in time and also further back. Okay, the detectors involved for probing the very early universe, the space-based LISA array, what we call pulsar timing array. I didn't want to use an array with LISA, but the space-based LISA, the pulsar timing array, the cosmic microwave background radiation, and we can do experiments with polarization to find information, and into the far future, next generation space-based interferometers. For the CMB era, the detectors will be LISA again, pulsar timing arrays, the cosmic microwave background radiation itself, because there are indirect signatures in there about events happening before CMB. And that shows up as patterns in the CMB, the cosmic microwave background radiation that we see. And the detectors involved, again, will be LIGO, Virgo, CAGRA, the Cosmic Explorer, Einstein Telescope, and LISA. Okay, so I'm going to show like 3 graphics just kind of quickly here that kind of show the history of the universe. There was a period of very rapid expansion called inflation. That kind of smoothed out information. So how far back can gravitational waves see? To be determined, okay? And I already mentioned the cosmic microwave background, which was at about 300,000 years of age for the universe. And now we're at about 13.8 billion years. Free electrons scatter light prior to the formation of the first atoms. There's about a 1,000-year slice there because it didn't happen all at once. It took a little while for everything to happen. Snap of a finger in cosmological time, though. Okay. Inflation will generate some gravitational waves that will be imprinted as characteristic signatures. This is really kind of exploring the same concept, just from a different frame of reference, featuring detectors involved. So if you look at this, where you see the ranges, quantum fluctuations of the early universe can be detected by a number of detectors. Binary black hole mergers can be detected primarily by pulsar timing and space interferometers. Particularly strong ones can be detected by the ground-based detectors. So the supermassive black holes are more the pulsar timing and space interferometer. The compact binaries are more typical black holes, can be detected by our ground-based interferometers. And we can also detect objects captured by supermassive black holes and rotating neutron stars in the indicated domains, okay? And this is showing the age of the universe. So we're trying to throw a lot of information into one chart. It doesn't always necessarily mesh as cleanly as we're showing it. Okay, and this provides some of the same information, but this time it's focusing on the in spirals and different epochs, the inflation of the universe, and so on. So, what can we see with just one LIGO detector? Well, if you have a black hole merger, and we're going to assume an event happened near the star Mizar in Ursa Major. What's going to happen is the detection is going to be discovered, and someone's going to yell, "Hey, there's a chirp." Where'd it come from? And they're not going to know. It could be anywhere in practically the whole sky. With 2 detectors, say LIGO Hanford and LIGO Livingston, the localization area becomes a broad ring, making a great circle on the celestial sphere. And here, since Ursa Major is a smaller sky patch, we're just seeing an arc of that circle on the celestial sphere. Why is it a circle on the celestial sphere? Because it relies on timing difference between when the signal was detected by LIGO Hanford and when it was detected by LIGO Livingston. And if you point backwards towards the celestial sphere, that timing distance could only happen from certain arrangements, and that arrangement tends to be a ring across the sky. So the localization area for the ring is approximately 1,000 degrees squared, and it's a somewhat skinny swath, but it's spread all the way around the circle, and that's how you add up to 1,000. Okay, so we still don't know where it was, and say if the event happened in Mizar, you could regard it as having equal possibilities of being anywhere along that ring. And in that scenario, the wave would, say, hit Hanford a few milliseconds before it hits Livingston. And that's the information that we would use to determine the timing difference and determine where in the sky those timing differences could have come from. Every point in the ring gives the same delay. Now let's add Italy's Virgo detector. So the long baseline, Virgo's a bit farther away, so the long baseline between one of the LIGOs and the Virgo detectors will allow a skinnier swath. And so what you see here, the first swath that you see is the swath created by the two LIGO detectors working together. The second swath that you see is the swath by Virgo and Pickett, one of the LIGO detectors. Because of the long baseline between that detector and Virgo, you're going to get a skinnier swath. But the nice thing is those two swaths, the blue one and the yellow one, they cross each other. And so now your localization is much smaller. It is where they intersect. So now for this event that happened in Mizar, we see it as happening in a patch of sky that is fairly close to Mizar. Now, using those two baselines together, the localization of the patch becomes 100 degrees squared, which is about 10 degrees by 10 degrees. So still a large region, but it's much smaller than the whole sky. Okay. The thickness of well, it's between 100 and 1,000, depending on relative angles between the events. The thickness of the swath is determined by how precisely the arrival time difference can be measured, the length of the baseline between the two detectors, and the orientation of that baseline relative to the incoming wave. So even though the detectors in the LIGO triad are in place, the gravitational waves can come from anywhere, and the orientation is going to vary from wave to wave, and our Earth is rotating, and we're going around the sun. So those orientations change over time. I don't know if I mentioned that small patch is often called a banana diagram because you have a skinny arc shape that's cut off And so you have a little small curved arc-shaped thing, and some scientists decided that it looked like a banana, so they considered that as a banana slice. Okay, if you use the all three of the baselines, the one between say LIGO A and Virgo, the one between LIGO B and Virgo, and the one between the two LIGOs, your swath will become, they'll intersect even more, and the localization area will become smaller, but not dramatically so. You've already got most of your bang for your buck. If you were to add similar Virgos around, they would shrink the patch size, but not dramatically show. So most of the bang comes from having three detectors. Okay. So what if we were to put a LIGO on the moon? For some reason, I thought of To the Moon, Alice. I don't know how many of you remembered. I imagine a fair number of you remember Jackie Gleason's comments there. So lunar LIGO, here's some conversations about it. It's a great idea, but things get complicated. Maybe someday. It's talked about from time to time, but not currently planned. We're going with Lisa instead. So the thing about a lunar LIGO is it would be helpful because it would give us very long baselines, and using all three of the baselines, our localization patch could shrink to about a degree squared, which is pretty small. However, placing LIGO on the moon would be difficult. Even though we always have the same side of the moon facing us, it would be difficult just in terms of creating that kind of structure on the lunar surface. And pardon me? Someone said something, but I didn't hear it. Well, anyway, so it's not entirely ruled out. It might happen someday, but Lisa, as we're going to see, does everything or will do everything that we want. So however, if we had the lunar logo, the lunar LIGO, and we had a neutron star merger, it would pretty much nail it, because if you got within a degree, you're going to be able to find it. Within a degree squared, you're going to be able to find it. Okay. So now I have a couple characters. One is a kind of a disgruntled scientist, and one is a talking cloud. And they're going to have some conversations from time to time, which is going to help us to understand a couple concepts. So who is this Lisa that everyone keeps talking about? She's the laser interferometer space antenna. What? Her arms are 2.5 million kilometers long? Oh, I was supposed to say that before. She's the laser interferometer space antenna. Cool, now we're talking. She's going to blow away LIGO, maybe, but she's built for a different task. Okay, so we're going to have these transponders in space that are separated by 2.5 million kilometers. They're going to act like LIGO does with say LIGO Hanford, with the two arms. They're going to allow us to make detections, but these are separated in space, where we're relying on the signal between them to effectively be the arms. So even though LIGO's arms are millions of kilometers long and made of empty space, they stretch and squeeze under a gravitational wave, just like LIGO's arms. LISA is not part of a constellation like LIGO A, LIGO B, and the Virgo triad. But hey, LISA's arms are really long. So she consists of 3 spacecraft, each carrying 2 free-floating test masses that act as laser transponders. The test masses stay in perfect free fall. The whole constellation is orbiting the sun. And a passing gravitational wave changes the distances between them. A passing gravitational wave changes the optical path lengths between spacecraft, producing phase shifts in the laser light. Those shifts reveal the wave's frequency, phasing, evolution, and timing. LISA uses active transponders instead of mirrors, because if we use mirrors, the reflected laser beam would spread out and become too weak over millions of kilometers. So the disgruntled scientist, okay, so her arms are 2.5 million kilometers long. That's 6 orders of magnitude bigger than LIGO. She must absolutely crush LIGO at localization, right? Thinking cloud. Not quite. LISA isn't a bigger LIGO. She's a different kind of detector. So this little L represents LIGO and the 3 squares represent LISA. LIGO localizes sources by comparing arrival times between separate detectors. Give LIGO more detectors or longer baselines, and the sky path shrinks. It's classic triangulation. LISA doesn't do that. LISA is one detector, a single triangular constellation orbiting the sun. Her 3 spacecraft don't give 3 independent arrival times. Instead, LISA listens to the gravitational wave for months while she orbits the Earth, cartwheels her triangular shape, and watches the wave from every possible angle. The motion imprints Doppler modulation, amplitude modulation, and polarization modulation into the signal. All of that information can be taken together and allow LISA to figure out where the source is. Did I mention that gravitational wave astronomy involves a lot of math? So LISA's arms aren't long, so she can triangulate better. They're long so she can hear low frequency waves that LIGO can't hear at all. So LISA's arms are only 2.5 million kilometers long. Can't we do any better? How about galactic scale detection? What? How? Just to get to the nearest star, 4.3 light years away, would take at least thousands of years, if not tens of thousands of years. How could we ever build something that big? We don't have to build anything. Gravitational wave detection is all about timing. And pulsars give us exquisitely precise timing from all over the sky. So in LIGO, the end mirrors mark the ends of the arms. In a pulsar timing array, the pulsars play that role, scattered across the galaxy, so that the Milky Way itself becomes the detector. And I have a couple charts that are have way too many words in them. But the
Jeff, let me
yes.
interrupt just for a second. I need to do a time check here. It's 9 o'clock.
Okay.
We've gone way over our time.
I had no idea that we're in that time scale.
Yeah.
Let me just show you like this chart and one other one. Okay.
Okay.
If you can imagine a small black hole orbiting a large black hole, the small black hole is so small, so very tiny that it is effectively exploring the fabric of space around the large black hole. And we're going to be able to get information about the nature of the space-time, which can actually be applied to test different alternate theories of general relativity. And one thing that is going to be detected that separates some of those theories is whether or not black holes can leak out some information, and they call that hair. So this little joke is, excuse me, sir, I'm having a bad hair day. And the little one says, I'll check. He really is checking as he goes through. And then my final chart, which was my joke chart. Okay, are you ready? You see all the equations that have to do with gravitational wave science and general relativity. And then I throw a shovel across it because the physics gets very deep very fast. So I think we lost some of that time in the beginning because I was trying to find out why things were frozen. But I also think I underestimated how long it would take to do the presentation. So, done.
Any questions? Thank you, Jeff.
You're welcome.
Jeff, this is Dave Jopi. Can you hear me?
Yes, I can.
You mentioned continuous gravity waves
Yes.
earlier. What's the source for that?
So the one source would be if you have a neutron star which rotates, and if its surface has a bump on it, then just like my asymmetric egg was going to create a gravitational wave as space tries to readjust to the shape of the egg. The little bump, they call it a mountain on the neutron star, would do a very small little distortion of space-time because space-time is going to try to change to account for that little distortion. If the black hole were completely smooth, there wouldn't be that distortion. So that's one type of signal that you would get it. And the other way you could get a pseudo continuous wave would be if you're in the very early phases of a merger, so that the waves are appearing periodic because we just haven't watched the event long enough to see the frequency changing.
Okay, thanks, Jeff.
You're welcome. Anybody else?
Are you going to make all the slides available?
I will. What's the best way to do that?
We can post them on the website, I believe.
Okay, we can do that.
And then the recording of this will go up as a YouTube video.
Okay. Well, I thank everybody for listening in, and there's some cool stuff that we didn't get to, but we will have the slides available. So thank you for the opportunity.
Thank you very much for doing this, Jeff. Greatly appreciate it.
Yeah, I'm going to undo the share and see faces or you're probably going to be. Ah. How do I undo that share?
There should be the share button should be stuck. There should be a red
yeah, for some reason I'm not seeing the bottom row of of commands. So, yeah, we won't worry about it. I'll just remain hidden.
All right, thank you. Thanks everybody for attending.
And have a great
Yeah,
weekend. Enjoy the Super Bowl if you're
Yes,
a
that's
football
right.
watcher.
Good night, all.
Okay, good night.
Jeff, thank you again.
You're welcome. Take care.